Welcome back to AI.Code.Cast. Today, we're doing a deep dive into a classic coding interview problem,
Yeah,
the min stack.
yeah, Minstack.
Have you seen this one before?
Oh yeah, it's one of those problems that seems deceptively simple
Right.
at first, but then as you kind of dig into it, it
Right.
can be a little tricky.
So for our listeners who might be encountering this for the first time, what exactly is a min stack?
So think of it like a regular stack. You can push elements onto it and pop them off, always accessing the most recently added element.
Yeah.
But a Minstack has this added superpower, you can say,
Okay.
where it can tell you the smallest element that's currently in the stack in constant time,
Okay.
no matter how many elements are in there.
Okay, so it's not just about storing the elements, but like finding the minimum value like super fast.
Yeah.
Why is that so important?
So you can imagine scenarios where you need to keep track of the smallest value that you've seen so far. Maybe you're like monitoring stock prices, analyzing sensor data, managing some type of resource.
Right.
Being able to retrieve that minimum value in constant time, which we call O1 complexity,
Yep.
can make your algorithms significantly faster.
Yeah, so it's like you're saying, it's not just a theoretical exercise.
Right.
It has like practical application.
Exactly.
And I bet interviewers love this
Oh, interviewers love this one.
because it tests your ability to think beyond just the basic stack operations.
Yeah, exactly. It forces you to think about how can we augment a simple data structure
Right.
to provide additional functionality without sacrificing efficiency.
Right. Okay. So let's say we're in a coding interview and we're hit with this min stack problem.
Okay.
What's like the first approach that comes to mind?
Well, the thing that pops into a lot of people's heads is the brute force approach.
Yeah.
And this is, simple to understand, but doesn't quite meet that efficiency requirement.
Right. Okay. Well, let's walk through it just to set the stage.
Yeah.
How would you implement a min stack if you weren't worried about speed?
So imagine you have your regular stack to store your elements right.
Yep.
So every time you're asked to find the minimum,
Yeah.
you would just go through the entire stack element by element,
Right.
comparing the values and keeping track of the smallest one.
Okay. Yeah. That makes sense. It's straightforward to implement, but I can already see the problem.
What's the problem?
If your stack gets really big,
Oh, yeah.
it's going to take forever to find that minimum value.
Right.
If you have to go through the whole thing every single time.
Yeah, exactly. So as your stack grows larger, finding the minimum this way becomes slower and slower.
Right.
You're essentially doing a linear search every time.
Right.
Which gives you a time complexity of O(n),
Yeah.
where n is the number of elements in the stack.
Okay, so that's not good.
And remember, we want that magical O1 complexity.
Yes, constant time, no matter how big the stack gets. So how do we move beyond this brute force approach and start thinking about more efficient solutions?
Yeah.
Like, what's the first hint you would give someone who's stuck?
Well, I might ask them this. What if we could keep track of the minimum value in a way that doesn't require us to scan the entire stack every time?
Oh,
What if we could store the minimum value like separately and just update it
Got
as
it.
new elements are pushed and popped?
Interesting. So it's like keeping a running record of the smallest value.
Exactly.
A running record.
But how do we actually implement that? We need to somehow efficiently store and update this running minimum alongside our main stack.
Right. So have you considered using 2 stacks instead of 1?
Ooh, 2 stacks.
2 stacks.
But how would 2 stacks help us solve this problem? Like, what would each stack be responsible for?
So think about it this way. 1 stack is going to be our main stack, right?
Okay.
It's going to hold all the elements in the order that they're pushed.
And then the other stack is going to be our min stack, which is going to be specifically designed to keep track of the minimum values.
Okay. I'm starting to see the light here.
All right.
So as we push elements onto the main stack, we would also somehow update that min stack to maintain the minimum. But how exactly do we keep them in sync?
So every time you push a new element onto the main stack, you compare it to the top of the min stack.
Okay.
And if that new element is smaller than or equal to the current minimum, you push it onto the min stack as well.
I think I get it.
Okay.
So the min stack isn't just a copy of the main stack. It's like a filtered version.
Yeah.
It's only the potential minimums that we see
Exactly.
as we push elements on.
Precisely. And the beauty of this is that the pop of the min stack will always hold the current minimum value of the entire stack.
Wow. That's pretty elegant.
It is.
So we've separated the concerns of storing elements and tracking the minimums
Right.
into two separate entities. It makes everything much cleaner, more efficient.
Exactly. And since we're just peaking at the top of that min stack and pushing onto the top of the min stack,
Right.
all of our operations remain constant time, that O1 complexity.
Okay. I really like this two-stack approach.
Yeah.
It's clever, it's efficient, and I can see how it solves the problem.
Yep.
But you know me, I always have to ask, are there downsides? Are there any trade-offs we're making?
Of course. So the trade-off here is that we are using two stacks,
Right.
which means we're essentially doubling the memory usage
Ah.
compared to using a single stack.
So it's like we're trading memory for speed.
Yeah.
And in many cases, that's worth it, especially when performance is critical.
Especially if performance is critical.
But are there any other ways to implement a min stack?
Yeah.
Maybe a way to achieve that same O1 complexity without doubling the memory usage?
You're thinking along the right lines. There's another clever approach that uses just one stack,
Okay.
but with a little twist.
A single stack solution. Now I'm really curious. Let's dive into that next. A single stack for a min stack. I'm all ears. How do we make that work?
So instead of storing just the values,
Okay.
we're going to get a little creative with what we put in the stack.
Yep.
Each element in the stack is going to actually be a pair of values.
A pair. Okay, you've got me intrigued. What does each part of this pair represent?
It's pretty straightforward. The first value in the pair is, of course, the element itself,
Okay.
just like you would have in a regular stack.
Right.
The second value is the minimum value encountered up to that point.
Okay. So each element is like carrying around a little note saying, hey, I've seen all the elements before me, and this is the smallest one so far.
Yeah, exactly.
Okay.
That little note, or that second value in the pair, is what lets us perform the get-min operation in constant time.
I see. Okay, walk me through an example. Let's say we start with an empty stack and we push the number 5. What happens?
So we push the pair 5, 5 onto the stack.
Yeah.
The element is 5, and since it's the first element, the minimum so far is also 5.
Makes sense. Now let's say we push the number 2.
Okay, so now we compare the new value 2 to the current minimum, which is stored as the second value in the top pair of the stack.
Gotcha.
Which is 5 in this case.
Okay.
Since 2 is smaller, we update the minimum. So the pair we push onto the stack becomes 2, 2.
Okay, I see. So that second value in each pair is always tracking the running minimum
Right.
as we go. And this works even as we push more elements.
Absolutely. Let's say we then push the number 7.
Okay.
We compare 7 to the current minimum, which is 2, from the top pair on the stack.
Okay.
7 is greater, so the minimum doesn't change. We push 7, 2 onto the stack.
Gotcha. So the minimum only gets updated when we see a new value that's smaller than the current running minimum.
Right.
Okay, that's really clever.
Yeah.
But what happens when we start popping elements off? How does the minimum adjust as we pop things off?
That's the beauty of this approach.
Okay.
When you pop an element, you're not just removing the value.
Yeah.
You're also removing the associated minimum.
So it automatically reverts back to the previous smallest value
Exactly.
that was stored in the pair below it?
Yeah.
It's all built in. No extra calculation or searching needed.
Exactly. This is how we maintain that constant time get-min operation.
Yeah.
Even during pops.
I love it. Okay. This single stack with pairs approach, I'm really liking it.
It's a good one?
It's elegant, it's efficient, and we're using less memory overall than the two-stack solution.
Right.
But being a good coder, are there any downsides here?
Yeah.
Anything we should be aware of?
Of course. Always got to think about that.
Yeah.
While we're using only one stack,
Yeah.
each element now carries a little bit more information.
Right.
It's got that extra number representing the minimum.
Right. So fewer containers, but each container is a bit bigger.
Exactly.
Is that something to be concerned about?
Well, it depends on the application
Right.
and the scale of the data.
Right.
In many cases, the overall memory savings of using a single stack outweigh the slightly larger element size.
Right.
But if you're dealing with, extremely memory-constrained environments or massive data sets, it's something to keep in mind.
Okay. It's all about those trade-offs.
Always trade-off.
Understanding them is a key part of designing efficient algorithms.
Right.
Okay. We've talked about two pretty cool solutions to the min-stack problem.
Yeah.
But I have a feeling you have one more trick up your sleeve.
Oh, you know me too well.
Is there another approach we could use?
There's one more approach that I think is worth discussing,
Okay.
and it might surprise you. Using a linked list.
A linked list. Wait a minute. Aren't linked lists typically used when you need to insert or delete elements in the middle of a sequence?
Yeah, that's right.
Doesn't that go against the whole LIFO, last in, first out principle of a stack?
You're right.
Yeah.
Linked lists aren't usually the first thing that comes to mind when we talk about stacks.
Right.
But in this case, they can offer a unique perspective and a slightly different set of advantages and disadvantages.
Okay, you've got me curious. Let's unravel this linked list mystery.
All right.
How can we use a linked list to build a min stack?
So similar to the single stack with pairs approach,
Okay.
each node in our linked list is going to store both the value and the minimum value encountered up to that point.
Okay.
We can call this field minto here.
Minto here. Okay.
Yeah.
So we're embedding that minimum tracking directly into the structure of the linked list.
Exactly. And just like with a stack, we'll always be adding and removing elements from the top of our structure.
Okay.
But in this case, the top will be the tail of our linked list.
Interesting. Okay. So when we push a new element, we create a new node at the tail of the list.
Precisely. The new node's minto here
Okay.
will be either the new element's value itself,
Right.
if it's smaller than the previous minto here,
Okay.
or it will simply inherit the previous node's minto here if the new value is larger.
Okay. So each node in the linked list is like a link in a chain, and each link is holding on to its own minimum value, forming this running record of minimums as you move along the chain.
Perfect analogy.
Okay. Okay.
And just like with the other approaches, popping an element is simple.
Yeah.
We just remove the last node, the tail, from the list.
Right.
Since each node maintains its own minto here,
Yeah.
we don't need to recalculate the minimum.
Right.
The new tail's minto here will already represent the correct minimum for the remaining elements.
Gotcha. Okay. I see how this works mechanically, but like, why would we even consider using a linked list for this?
Okay.
What are the advantages over the other approaches we discussed?
Well, one key advantage is flexibility.
Okay.
With a linked list, you can easily grow or shrink the structure as needed.
Right.
You don't have to worry about fixed array sizes.
Right.
That might require resizing operations, which can be really costly in terms of performance.
Ah, yes. I remember those pesky array resizing issues
Yeah.
in my data structures class. So
They can be a pain.
with a linked list, we could potentially have better memory efficiency, especially if our min stack is constantly changing size.
Exactly. We avoid that overhead of allocating and reallocating memory for a fixed size array.
Gotcha.
And of course, all of our operations, push, pop, top, get min,
Yep.
remain O1,
Yeah.
just like the other approaches,
Time.
we're simply updating pointers,
Yeah.
which takes constant time.
All right. So the linked list approach offers flexibility and potential memory efficiency. Would you say it's the best solution?
As with everything in computer science, it depends.
Of course. Of course.
While the linked list offers that flexibility,
Right.
it does come with the slight overhead of having to manage the pointers between those nodes.
Yeah. Another trade-off.
Another trade-off to consider.
More flexibility, a bit more complexity in terms of implementation.
Right.
And I could see how the mental model of a linked list as a stack might take some getting used to.
Absolutely. It's all about understanding those nuances of each approach and choosing the one that best fits the specific requirements of your application.
Right. Makes sense. Now let's shift gears a bit
Okay.
and talk about why this min stack problem is such a staple of coding interviews.
Yeah, great point.
It feels like a relatively simple problem on the surface,
Yeah,
but as we've seen, there's a lot of depth to it.
there is.
What are interviewers really looking for when they ask about min stacks? It feels like, a relatively simple problem on the surface,
Yeah,
but there's a lot of depth to it.
there is. Yeah.
What are interviewers really looking for when they ask about min stacks?
I think it's a fantastic way to gauge a candidate's understanding of fundamental data structures and algorithms.
Right.
Do they really understand how stacks work? Can they think beyond those basic operations
Yeah.
and come up with creative solutions
Yeah.
to enhance functionality?
It's like testing not just your knowledge, but also how you can apply it
Right, exactly.
in a problem-solving context.
Yeah, and it goes beyond just, rote memorization of algorithms.
Right.
The min stack problem forces you to think critically about trade-offs.
Yeah.
Can you weigh the benefits of speed versus the cost of memory? Can you articulate those trade-offs clearly and justify your design decisions?
It's also a good test of communication skills.
Absolutely.
Can you break down a complex problem like this into manageable steps?
Right.
Explain your thought process clearly and concisely.
Yeah, because in a real-world coding environment,
Right.
You're rarely solving these problems in isolation.
Right.
So being able to communicate your ideas effectively to colleagues and explain your solutions clearly is essential.
It's essential for collaboration.
Exactly.
Okay, so the min-stack problem isn't just this technical puzzle.
Right.
It's like a way to assess your holistic understanding of computer science,
Absolutely.
problem solving, and even communication skills.
All in one.
Yeah, it really is a comprehensive test.
It is.
And for anyone listening who's preparing for coding interviews, mastering this problem is a good use of your time.
Oh, yeah, absolutely. It shows that you have, a good grasp of those core concepts and the ability to, think critically.
And creatively.
Yeah.
Well said. So to wrap up our deep dive into min-stacks,
Okay.
the key takeaway is this. Don't be intimidated by problems that seem simple on the surface.
Right.
Dig deeper, explore different approaches, and always consider those trade-offs.
Think about those trade-offs.
You might just discover a really clever solution that showcases your skills and impresses your interviewer.
And remember, the journey of exploring these solutions is just as valuable as the destination.
That's a good point.
The more you grapple with these classic problems, the stronger your problem-solving muscles become.
That's great advice. Well, folks, that brings us to the end of another episode of AI.Code.Cast.
All right.
We hope you found this deep dive insightful and maybe even a little bit inspiring.
Inspiring. Keep practicing.
Keep practicing, keep learning, and keep pushing those boundaries.
Push those boundaries.
Until next time, happy coding.